everybody. Thank you for being here. Welcome. Thank you for joining. Grab yourself a notebook, a pencil, or a pen if you're so bold. Anything you choose to write with is fine. This is math from the void. Math coming at you pretty much out of nowhere. And today we have a problem from the 2007 AP Calculus BC exam. And we also have a bit of a different approach because I'm sharing my entire window. Now we're going to approach most of these problems with doing as much as we can without the calculator because that's honestly my style. But then I am going to show you how to use the Desmos tool so you'll be able to see my screen and sort of what I'm typing in order to get some insights about the problem. I figure that's a decent balance because I'm not going to just have you rely on Desmos calculators. I want you to understand what you're doing. I want you to understand pre-calculus and not lose it. Several reasons why. I just prefer doing things sort of the old-fashioned way, you might call it. But in any event, give yourself about 12 minutes to do this problem. If you're in Calculus AB, you can absolutely answer this problem. It's from the BC exam, but it's definitely approachable by AB. I wouldn't be surprised to see a question like this asked on the AB exam. Yeah, give yourself, since you have a calculator, Desmos at your disposal, give yourself 10, maybe 12 minutes. Yeah. And then when you're ready, join back and see a nice thorough explanation by yours truly here. All right, let's get started. So R is the region in the first and second quadrants, bounded above by this graph. We'll talk about that in just a moment, and bounded below by y equals 2. So, of course, we have Desmos, but it's really important to know what this looks like. There's y equals 2. This is like a bell curve function. If you plug in 0, you get the maximum of 20, which is going to be like, pretty high up. It's even because if x is negative or positive, you get the same answer. And as x gets bigger, the denominator gets bigger. So that means this gets smaller. It's going to make a bell curve kind of a shape. And it's probably not symmetric. Of course, my hand drawings are not necessarily going to be symmetric, but it is going to meet at some point. Because as this thing approaches 0, it'll hit y equals 2 at some point. Okay, find the area of R. Well, that's really easy now that we have a drawing of it. We're just going to be doing some rectangles dx with respect to x. So top minus bottom function is the name of the game. That's how we find the area using integral. We need the integral of starting point to stopping point. It's negative something to positive something. We'll figure out what that is in a moment. Then we have the top function, which is 20 over 1 plus x squared, minus the bottom function, which is just 2. And this is all going to be dx. Now, putting parentheses, I'm starting to do that now because this is how you're going to plug it in to Desmos. Let's find out where exactly this crosses. We can find where they cross. Again, you could use Desmos. Do not rely on the crutch, though. We're going to have 20 equals 2 plus 2x squared. Therefore, 18 equals 2x squared. And therefore, 9 equals x squared. So this is plus or minus 3. So I didn't need to plug that into a calculator. You shouldn't need to plug that into a calculator. So there you go. You get some points for setting up that integral. And now we'll use Desmos to get a value for it. So in order to use the integral, you type in int, and it kind of just knows that you want to do an integral. Really important here, put some parentheses. First thing you do, put parentheses. Just do it. First thing you do. Because otherwise it's not going to detect what's going on here. If I try to do 20 over 1 plus x squared, and then put minus 2, and then say, hey, but I wrote a dx, why isn't the calculator reading my mind and understanding exactly the way I want it to understand? And, well, because you can put a dx at the end of here, but that would just give you a value for the integral there. So we need the parentheses in the front, and minus 2, and then with respect to x, and you get your answer 37.96. 18308959. See if we can copy and paste that here. There's our value. See how fast we can do this with Desmos. We can definitely do some of these things pretty quickly. Now for part B. Find the volume of the solid generated when R is rotated about the x-axis. So what we're going to have to do now is we're going to have to three-dimensionalize this. And we're going to get some washers out of this. How do we know we're going to get washers? Well, that's because the boundary, the bottom boundary, is not the same as the line we're rotating it around. So we're rotating this shape around a boundary, which is, a line which is not one of the boundaries, which means that you're going to get this sort of like bigger circle out here. We're wrapping it around the x-axis. And then underneath that, you're going to get this sort of like hole that also wraps around. So each slice is going to look something like this. Oops. Halfway, and then halfway, okay. And then we have this hole. You can notice that as these two boundaries get closer to each other, then the hole is going to be more pronounced inside. But generally what we have here is we have this bigger circle on these slices, and we have this inner circle, smaller one. Then we have the x-axis right there. So here we're going to get the large R, capital R. That's going to be 20 over 1 plus x squared. That's the radius of those slices, the big radius of the slices. And then we have the little radius of the slices. So this is little r equals simply 2. That's the distance here from that boundary to the rotational axis, whereas the large distance is the height of the top function. Makes sense, right? And each of these slices has area in here, but we've removed the inner area. So here we have a equals pi big R squared minus little r squared. Of course, technically it's pi big R squared, which is the area of the big circle, minus pi little r squared, which is the area of the small circle. And we don't just want these slices. We want to add all of these slices up. We want to add them all up from -3 to 3. That's going to cover all the slices for the region. And 2 squared, you could just put as 4 if you wanted to. So our volume is going to look like this. I might as well just type it into Desmos to show you guys what that's going to look like. Pretty similar, actually. Bam, squared. And then I'm just going to call that 4, because why not? And then don't forget, we're multiplying this by pi. That's going to give us 1871. If you don't have that, your answer is going to be off by a bit. So 1871.19. In fact, I'm actually going to do one better than that. I'm going to copy and paste this whole little thing here. It has the integral expression and everything that you need, so I think it's useful to put it like that. And there is our answer. So easy, so fast. Could this be done by hand? Possibly, yes, it could be. Do I want to do it by hand? Absolutely not. Just in the interest of time. I would love to do that on my own free time, while I'm on a beach in Hawaii somewhere. Sure, I'll do some integrals just for funsies. But for now, we're talking serious business. We're on a time crunch. Let's look at part C. The region R is the base of a solid. For this solid, the cross-sections perpendicular to the x-axis are semicircles. Find the volume of the solid. Okay, so let's see. This was part B. Does it make sense what we're looking at here? It says that the cross-sections perpendicular to the x-axis are semicircles. So that means that the diameter is in the region. Let's take a look at that. I kind of want to graph this again, just because. So here we have bottom line. Meets with that, that kind of a thing, right? And it is technically going to keep going further, this one. But anyways, let's three-dimensionalize this. Bam. Bam. And so each of these shapes that are sort of sticking out at you, it's as if like a semicircle, like half a record collection or something, like half of the records are sticking out in their place or something like that. So we have this here, and it's going to make a semicircle that comes out. I guess I can do something like this. And then here are the smaller ones. So here they stick out. They kind of come out at you. I know it doesn't look very convincing, but they're sort of coming out at you. Kind of like, I don't know, fins or gills of a fish if you're looking at the side of a fish. So let's get a better drawing of what this actually looks like. So here is the, or maybe I'll draw it vertically. If we were looking at it sideways and not this weird slanted view that I've given you, we'd be looking at pieces like that. You know what I mean? Like if the wall were right on your right side, that region was like the wall, you'd be like looking at these. And they're getting bigger depending on if that gap is getting bigger. So here is the diameter of these semicircles. The diameter is simply top minus bottom function. That means the radius is half of that. So we have 10 over 1 plus x squared minus 1. That's the radius of one of these. And of course, the area of one of these is half of the pi r squared. In other words, half of pi times 10 over 1 plus x squared minus 1 all squared. That is the area. So let's find the volume. I think it says find the volume, and did it say anything else? Nope, just says find the volume of the solid. Okay, pretty straightforward. Let's put that into Desmos. So we're going to have 1/2, still integral from -3 to 3, but now we're going to have 10, and we're going to have minus 1, and that's all going to be squared. All right, there we have it. We didn't even need to really graph with Desmos at all in this one. It was pretty straightforward. Now, I'm not saying you can't use a graph. I'm not saying that. I'm saying you shouldn't need it for certain problems. This is one of those. And I also just, highly encourage you using as much of your own pre-calc skills, calc skills by hand as possible to get your answer. Yeah, so that'll do it. This new approach where we're using Desmos, incorporating Desmos, is something that we just need to adapt. We need to adopt, rather, because we need to adapt to the new format of the exam. And I want you all to be competent in calculus, regardless of whether or not you had a calculator or, a stick to carve stuff into the sand as your notebook to write on. Like, you should be able to do this math regardless of what materials you have, up to a certain point. Of course, they're not going to have you take crazy integrals by hand. But some of these problems, you have to set up the integral. You don't necessarily need to even solve it. Okay, I think that's enough blab out of me. The nice thing about Desmos is you don't have to worry about rounding. If you plugged it in correctly, it's going to get the whole freaking decimal. So, yeah, there's no confusion on how many sig figs I need. That's the exact answer. And it also kind of shows exactly how you got that answer, which is, I guess, pretty convenient. All right, yeah, that's enough blab out of me. I'll see you guys next time.